Hello class, my name is Ian and I will be teaching you about Euler's method. Euler's method allows us to approximate the values of an integral curve using multiple tangent lines. To do this, we have to utilize linear approximation. Keep in mind that a smaller step size will increase the accuracy of our approximations as there will be a larger amount of tangent lines. Now let's say that we have a differential equation y prime equals x plus 2y, and the initial term of y of 0 equals 1. Our objective is to find f of 0.75 if there is a step size of h equals 0.25. Euler's involves using linear approximation multiple times to find close values to the actual line. First, let's plug in the initial condition into the differential function. Then, since we know the derivative, we can create a tangent line by using point-slope form. Then, since we know the derivative, we can create a tangent line by using point-slope form. So, if the next step's h equals 0.25, we have y of 0.25. So this will ultimately equal, if we put into point-slope form, it'll be y minus 1 equals 2, the slope from y prime of 0, times x minus 0. Now we can reformat this as y equals 2 times our x value of 2.25 minus 0 equals 0.25 plus 1 from the other side. And this equals 1.5. So after this, we have our first step point of x equals 0.25 and y equals 1.5. So for the next step, we'll use these values right here to approximate the next tangent line, or the next step. For y of 0.5, or the next step, we just use this same idea of linear approximation. So we have our derivative function, and we plug in, rather than plugging in the initial value of 0, 1, we just plug in what we just found as for our derivative function. So we plug y prime equals 0.25 plus 2 times 1.5, which equals 3.25. Now we can create the next tangent line using point-slope formula. So we use, now we can find the next tangent line using point-slope formula. So we do the previous steps values, so y minus 1.5 from here equals 3.25, which was the found slope, times x minus 0.25, which we can reformat this as y equals 3.25. And then if you plug in x of 0.5 right here, we'll just get 0.5 minus 0.25, which equals 0.25 again, plus 1.5, which equals 2.3125. So that means our next step's value of y of 0.5 will equal 2.3125. Now to find the last step of y of 0.75, we just do the same exact steps as the first two steps. So we find the derivative to be 5.125 at this point. And if we plug in point-slope form, we'll get y minus 2.3125 equals the slope times x minus the previous x term. And we can reformat this as y equals 5.125, 0.25, plus the previous x term. And this number should equal 3.594. And that is y of 0.75. So the approximation using Euler's method is 0.75, which equals 3.594. Now, if we look back on the three equations, you may notice something similar about each one. Euler's can be simplified into the derivative times the step size plus the previous y value.
Before I start with the practice problems, I just want to review the basics of logistics. So let's start with a differential equation because that's usually what you're given in problems. And the equation is dp over dt equals little k, a constant, times p, multiplied by 1 minus p over big K, which is the carrying capacity of the population. And over here on the left, you'll find that A equals big K minus initial population all over initial population. And that'll help you over here with finding the equation for a population at any given time, t. And that equation is big K over 1 plus A over here times e to the negative k times t. And on the right, you'll find the graph for a population. And the limit as t approaches infinity, or as time approaches infinity, for any population will always go to the carrying capacity. First problem on the worksheet, that is the logistic problem, is number 4, and it says that a population of fish is modeled by dp over dt equals p times 30 minus p over 2000. Now, there's something different in this equation from what I stated earlier, and I'll give you guys about 5 seconds to figure it out for yourself. Now, if you didn't figure it out, it's here where it says 30. Now, in the original equation I gave, I said that little kp times 1 minus p over k is the differential equation. But here, that's a 30, not a 1. Now, if you continued with the problem like this, you would have gotten it wrong. And it's very important that this equals 1, otherwise you can't get to the population model. So what should you do? Well, you have p times 30 minus p over 2000, and you just want to get from 30 to 1. So what you would do is you would multiply by 30 over 30. And you can do this because this is basically just 1. And what happens is you would distribute the 30 over here, so 30p multiplied by 1 over 30, which is right here. So you would get 1 minus p over 60,000. And now you have this format with little k equals 30 and big K equals 60,000. Now you can continue on with the problem. So in part A, it asks, what values of P is the population increasing? So P is increasing when population is less than the carrying capacity, right? So if you look at a graph here, let me make sure you guys can see that, yeah. So you have K here is the carrying capacity. If you start below it, population will increase until K. But if you start above, it'll decrease towards K. So if you're not given an initial population, you just have to answer it generally. So what values of P is the population increasing? P is increasing when it is less than K. And in this case, K equals 60,000. Likewise, for part B, what values of P is the population decreasing? It's decreasing when P is greater than K, which equals 60,000. In part C, it asks, what is the equilibrium solution? Well, if you don't know what that is, it's just a fancy way of saying what is the limit as t approaches infinity of P of t. And if you remember, this will just always equal K. So in this case, the equilibrium solution would be 60,000. And that is it for number 4 on the worksheet. You may also be asked to state when the population is growing the fastest. And this is usually when the population is half of the carrying capacity. And so the initial population starts below the carrying capacity, then halfway to the carrying capacity, population is growing the fastest. However, if you look here, if the initial population starts above the half of the carrying capacity, then the instance where the population starts, that is when it is growing the fastest. And if the population starts above the carrying capacity, then wherever it starts is also where the population, well, it's not increasing the fastest, but it is changing the fastest at that point.
Wow, I can't believe you made it to the end of the video. Thanks for watching, and I hope you ace the next test.